Talking about matching energy, this bitch is killing me. Talking about.
Relatively similar.
And for Valentine's.
Excuse me, Professor. I think you might be muted.
Professor, you're muted.
Okay, I was muted. There's a newbie beginner mistake. So welcome to oceanography. And we're going to be talking about atmospheric circulation, chapter 8 this week. And next week, we'll talk about oceanic circulation, chapter 9. A lot of the principles that we'll go over in this week will come back again in a different form in chapter 9. So the main points that we're going to be absorbing as we read through chapter 8 and try to grasp an understanding of this are the way in which the unevenly heated surface of the ocean sets in motion, of the Earth sets in motion air masses, and the way that the Earth's rotation through what's called the Coriolis effect imparts acceleration, secondary accelerations on the path of these moving air masses. We'll talk about storms, the storm system, the interaction of how the interaction of the ocean and the atmosphere moderates surface temperatures. So main points: uneven heating, moving air and heat. conservation of mass, and the way in which Coriolis effect adds a twist to all motion, and how these basic effects, differentially heated planet, conservation of mass, Coriolis effect, these different effects that produce the patterns of weather and climate. Now, weather is chaotic on small scale, but climate is predictable on an annual basis. We know that the winter is going to be cooler than the summer. But these patterns are changing over time, and they're changing in response to human effects. So the first thing that we have to remember when we're thinking about heating is what the components of heat are. We talked about the way in which heat is different from temperature, and the way in which heat is an input of energy, most of it arriving from the sun. So if we heat a fluid body, whether it's water or air, the source of the heat is radiative heat arriving from the sun. Convection, which is circulates water mass. So if we think of a heated, think of a pot being heated by radiation from a stove, the bottom of the pot, the water at the bottom of the pot will heat more rapidly than the water at the top of the pot. Okay, and the heat is lost from the system through latent heat and conduction. By latent heat, I mean the steam which comes off of the water is water vapor, and that water vapor has required 540 calories per gram of latent heat to be input in order to break down the chemical bonds, the molecular bonds between the water molecules, and allow water, liquid water, to behave as a gas. So that latent heat is being removed from the system. The other thing that's occurring is conduction and convection. Conduction is the process by which heat is transferred within a body. And so, conduction is the process which is going to heat the handle of the pot by heating the steel and allowing the heat to travel conductively through the body to your hand. And conduction also allows heat to be transferred from within the water. So why does the water move within the pot? Well, the warmer water at the bottom of the pot is less dense than the cooler water. So the cooler water at the top of the water of the pot, toward the top of the pot, wants to sink down and displace that cooler, warmer water. And so this process of sinking and rising imparts motion to the water, and you can observe that by watching the motion of water in a pot. So we can think about this in terms of a pot of water heating on a stove. We can also think about it in terms of water and of heat in the atmosphere. So if you have lots of sun and lots of rain, the heat from the sun evaporates the water and creates buoyant masses of moist, warm air. So this is a picture from a cloud forest. This was in Mexico, in a place called La Selva. This is an altitude of about 4,000 feet, so it's up, but it's tropical. And so when I took this picture, it was fairly early morning, and to begin with, the whole region had been foggy. You couldn't see this hilltop. And then gradually, as the sun began to warm the air, the clouds lifted and eventually lifted above the valley. And when they reached a certain altitude, it began to rain. And this process of convection and conduction allowed heat and air to circulate within this valley. So that process is going on small scale and large scales across the planet at all times. Well, let's look at where the properties, and let's explore more deeply the properties of uneven heating of the planet. So the Earth as a whole is in thermal equilibrium. So all of the heat which arrives, all the energy which arrives to the Earth is eventually transmitted back into space. So there's an equilibrium with the incoming solar radiation. But that, if that's for the whole of the planet, but the equatorial regions, the low latitudes, are heated to a greater degree than the high latitudes, the north and the south pole and Arctic regions. And so in order for the whole of the planet to be in equilibrium, the heat that unevenly arrives, the excess heating at the equatorial region, has to be transmitted or transferred from low latitudes to high latitudes. And this happens in terms of moving currents of air. So we can look at this in terms of net radiation surplus and net radiation deficit. So there's a surplus of radiation at the low latitudes and a deficit at the high latitudes. And this uneven heating is one of the principal drivers for movement of air, and with the movement of air, the change in local changes in weather and climate. So why is the unearth? But it's not just that the Earth is unevenly heated, but that the way in which this uneven heating of the Earth changes with season is a result of the tilt of Earth on its axis. So recall that the Earth is tilted at about 23.5 degrees relative to the elliptic, the path that it translates around the sun. So if we think about the radiation that's arriving at the Earth, and so the radiation is constant as it moves through space, but it's impacting a circular or spherical body into the Earth. So at the equatorial region, the radiation is concentrated in a finite area. But as you move further to the north or further to the south, the angle at which that constant flux of heat strikes the Earth increases. And with that increasing angle, the amount of heat arriving at any unit area on the surface decreases. So there's a higher density of incoming heat at the equatorial region, and a lower density as you move higher into on the Earth, going from the low latitudes to the high latitudes. Okay, so this would be the same for any portion on a spherical surface, but remember that the Earth is rotating around an axis which is tilted at approximately 23.5 degrees. So that means that, and then this tilt remains constant as the Earth completes its orbit around the sun. So that at certain times of the year, the sun staying in one place relative to the Earth, the heat concentration is more
got a legendary
pronounced in the northern. Please, Nelson, please silence your microphone. The heat concentration at higher northern latitudes is greater than it is in southern latitudes. So there is a northern hemisphere summer when the tilt of the Earth the northern tilt of the Earth is towards the sun. In the wintertime months, the tilt of the Earth replaces the southern hemisphere.
So you're now with a Mozambique shield.
More places the southern hemisphere more directly under this incoming radiation energy. So the energy flux is reduced when the tilt of the Earth decreases the angle at which the solar radiation can arrive at Earth. Okay. So this is showing this annual change in the uneven heating of the planet. So the Earth is unevenly heated in terms of its spatial orientation, and it's unevenly heated in terms of the annual cycle dictated by the planet's orbit around its sun. So we can look at this in detail here. So at the equinoxes in the northern and southern in the March and September timeframe, we could expect to have relatively uniform temperatures. And at the so interestingly enough, the southern hemisphere, the northern hemisphere, has its greatest tilt toward the sun in July, which is also the time of year when the Earth is farthest from the sun on its ecliptic. So we know that the Earth has an elliptical path, follows an elliptical path as it orbits the sun, but the proximity of the sun doesn't really change. It changes by, about 5 million kilometers, but that difference in distance doesn't account for the warmer temperatures in the northern hemisphere during summer months, because that summer month corresponds to the time when the northern hemisphere is when the Earth is furthest from the sun. So the tilt of the Earth is what controls the orbit, seasonal change in temperatures. And keep in mind this tilt, because we'll get back to tilt and thinking about tilt when we talk about how climate change and climate cycles are influenced by changes in this tilt. These changes in this tilt are part of long-term cycles called Milankovitch cycles, which cause tiny variations in the degree of this tilt. And with those tiny variations, we get long-term drivers on climate change. Okay, so the tilt of the Earth during its annual cycle produces a hemispheric pattern of warmer and cooler temperatures during the summer and winter periods, respectively. All right. So the incoming radiation, so the Earth, the stream of energy from the sun arrives at the top of the atmosphere. And at the top of the atmosphere, there's 7 million calories per square meter per day, averaged over the entire Earth. That's the average for any square meter. Okay? So as this energy arrives at the sun, 100% of it, some of it is absorbed by water vapor, some of it is absorbed by clouds, and some of it is absorbed by water and land. And some of it backscatters from the air, backscatters from clouds, is reflected into space. So outgoing here, approximately 30% is reflected back. And then the rest is released back into space as infrared long-range radiation, about 70%. So about 30% of the incoming radiation is reflected back as light energy, and about 70% of the incoming energy is reflected back into space as heat, as long-wave radiation. And since the Earth is at equilibrium, we can assume that the inputs and outputs of heat from the Earth have to be constant over any average period of time, even if there are local differences or regional differences due to the season. So let's think about, so this pattern here that we're talking about would suggest that we're going to have different regimes of temperature, depending on where you are in a profile of the atmosphere. So the atmosphere extends out to approximately 100 kilometers, although there's not much atmosphere left at 100 kilometers. And as we descend in that, the atmosphere is going to display very different properties. So one of the properties, and one of the things that we need to keep in mind, is that the pressure of the atmosphere increases or decreases with altitude. So the at any particular altitude within the atmosphere, the all of the gases in the atmosphere are subject to the pressure of the gases higher up in the atmosphere. So if we think about a parcel of air at 30 degrees C, and we raise it up to a higher level, that reduction in pressure is going to allow that parcel of air to expand. Well, as that partial of that expansion increase, as that parcel expands, there is a loss of heat. It's just as we, if we decompress something, there's a loss of pressure and a loss of heat. And so the air cools, and it continues to cool as the particles of air or the parcels of air rise higher into the atmosphere. Likewise, if parcels of air descend, they are compressed and they warm. So this property of warming and cooling due to compression or expansion is a source of heat which is independent of the incoming radiative heat from the sun. So ascending air cools as it expands, and cooler air can hold less water. So the water vapor condenses into clouds. So if you warm air at the surface of the planet, and if it evaporates, contains a certain portion of water vapor, and if that rises, then there's this loss of heat due to expansion, and with that loss of heat, there's less ability for the air to hold the water, and the air may condense as clouds, and those clouds may eventually become cool enough for the water to fall, to precipitate and fall as rain or other precipitation. So this property of this effect of rising and falling air parcels is one of the factors which induces weather-like conditions. So if we look at the atmosphere as a whole, we can take this these properties that we understand and divide the atmosphere into layers. And so this is the 100 kilometers, and so at the very top of the atmosphere, the incoming radiation is here. There are very, very few water molecules present, so it's very little air present. The atmosphere is quite diffuse at this point, and then as we descend further and further, the atmosphere gets denser and denser. So this chart here shows the approximate temperature in degrees C. So there's an important level at about 10 kilometers above the Earth's surface. And this region is called the tropopause or troposphere. The lower 10 kilometers is the troposphere. Above that is the stratosphere, the mesosphere, and finally the thermosphere. These are names that are given to these approximate regions of the atmosphere. Well, 90% of the weather and 90% of the atmosphere is within this tropospheric portion of the atmosphere. And so everything that, that's happening, the temperature is rising more rapidly as you descend. And, so interestingly, at the stratopause and at the top of the stratosphere, the temperature increases to around 0, and then decreases and then increases towards the surface, and then the surface of the Earth has an average temperature of about 15 degrees C. So the atmosphere is layered, and it's layered by temperature, density, and composition. And there's a cold cap at the top of the atmosphere, and the pressure will decrease more rapidly with height where the air is colder. Ozone, which is a component of the atmosphere, O3, absorbs a lot of the incoming UV radiation, and that absorption of incoming UV radiation is responsible for this change in temperature between the thermosphere and the mesosphere. So as the ozone concentration increases, we see a rise in temperature. So the atmosphere is layered. It's layered by temperature, humidity, pressure, and within these layers and between these layers, the movement of air causes distinct differences. All right, well, we want to talk about convergence and convection cells. So we talked about convection when we were considering the heating of water in a pot, and then we reviewed the fact that there is low pressure and high temperatures around the thermal equator. And so we would expect that with this low pressure and this uneven heating, there would be a rise, a general upward tendency of air that was heated at the equator. So this air is rising up. Well, here, when we start considering mass movement of any fluid, including air, when this fluid rises up, when this air mass rises up, it can't leave behind a vacuum. So there has to be a conservation of mass. We have to have a constant mass. And so as warm air rises, or it's actually displaced by cooler air, that cooler air is rushing in and is displacing upward the warmer air. Okay, so you get this rise, and then when the temperature equilibrates, it transfers. So a convection cell is set in motion by a temperature gradient at the bottom, which causes heat, air or water to warm, to become less dense, and then that less dense air or water is displaced by cooler material moving in from the side. So this convergence takes place at the equator. Now I've listed the equator here as 0 degrees latitude, but keep in mind that because the Earth is tilted on its axis, that 0 degrees is not always, the 0 degrees is with respect to the spherical Earth, but that 0 degree latitude is not necessarily, or the location of the thermal equator. So the thermal equator is the portion of the Earth which is in direct path of the sun, and so that's going to change over time. Now this region here, where there's convergence of fluid, of air moving in from northern and southern hemisphere, this is called the Intertropical Convergence Zone, ITCZ. So the ITCZ is the zone in which this is occurring. And the convection cells located to the north or the south of the ITCZ are called the Hadley cells. So if we think about, in the sort of a diagram of the Earth, there's low pressure at the inter ITCZ and a higher pressure on either side. So there's air moving toward the equator at the surface of the, towards the thermal equator at the surface of the planet, and so air is rising here, and then at the surface you have this northern or southern movement of air to displace that rising air. And likewise, further north, you have additional convection cells, which are set in motion by other movements. Okay, well, so if we, this is the map looking at this, if we look at a picture of these cells across a spherical representation of the planet, we can start to get a better sense of what's happening. So these are the Hadley cells. This is the intertropical convergence zone here. And it's typically, the intertropical convergence zone is typically a little bit to the north of the geographic equator. And so there are surface winds that are moving to the north in the southern equator, southern hemisphere, and to the south in the northern hemisphere. Okay. Well, all the time that this air is in motion toward the north or to the south, the Earth is rotating on its axis. And the rotation of the Earth on its axis is going to impart a relative motion of the air that's moving. And this relative motion is due to a process called the Coriolis effect. And so the Coriolis effect is, it's not really a force, but it's sort of a result of the fact that there is motion on a moving body. And so let's look at a few cartoons to try to get clear for ourselves how the Coriolis effect is influencing air movement and water movement. This is kind of a whimsical view of this, but I think it illustrates the different processes that are going on. So we think about a planet placed on a rotating disk, and so these balls are actually moving in a straight line, but because the Earth appears to be rotating, we don't know that we perceive them as curved. But if we start moving so that our frame of reference changes to the Earth's frame of reference, we see these curves exactly more fully. And we can draw the vectors of force onto those balls, and we see how they change over time. If we do the same thing with a pendulum, so the pendulum we know is translating back and forth. The Earth is rotating under this pendulum. If we switch to the disk's frame of reference, you'll see what happens. Instead of a straight line, there's an apparent circle of the pendulum. And some of you may have been in a museum. Sometimes they have pendula hanging from large strings. And so we can, observe how this apparent motion of the pendulum relative to the Earth's movement. So that was a look at physical processes of the Coriolis effect. And let's think about how they would affect the movement of air during large-scale storm events. So here's another video showing that.
If you've ever watched the news during a hurricane or wintertime nor'easter, you've probably noticed that big storms spin over time as they travel. In the northern hemisphere, they spin counterclockwise. But if you were watching a storm in the southern hemisphere, you'd see it spinning clockwise. Why do storms spin in different directions depending on their location? And why do they spin in the first place? A storm's rotation is due to something called the Coriolis effect, which is a phenomenon that causes fluids like water and air to curve as they travel across or above Earth's surface. Here's the basic idea. Earth is constantly spinning around its axis from west to east. But because Earth is a sphere and wider in the middle, points on the equator are actually spinning faster around the axis than points near the poles. So imagine you were standing in Texas and had a magic paper airplane that could travel hundreds of miles. If you threw your airplane directly northward, you might think it would land straight north, maybe somewhere in Nebraska. But Texas is actually spinning around Earth's axis faster than Nebraska is, because it's closer to the equator. That means that the paper airplane is spinning faster as well. And when you throw it, that spinning momentum is conserved. So if you threw your paper airplane in a straight line toward the north, it would land somewhere to the right of Nebraska, maybe in Delaware. So from your point of view in Texas, the plane would have taken a curved path to the right. The opposite would happen in the southern hemisphere. An object traveling from the equator to the south would get deflected to the left. So what does this have to do with hurricane spinning? Well, at the center of every hurricane is an area of very low pressure. As a result, the high pressure air surrounding the center or eye of a storm is constantly rushing toward the low pressure void in the middle. But because of the Coriolis effect, the air rushing toward the center is deflected off course. In the northern hemisphere, the volumes of air on all sides of the eye keep getting tugged slightly to the right. The air keeps trying to make its way to the middle and keeps getting deflected, causing the entire system to spin in a counterclockwise direction. In the southern hemisphere, where the Coriolis effect pulls air to the left, the opposite happens. Storms spin around the eye in a clockwise manner.
All right, so there's two cartoons or two videos to illustrate the way in which the Coriolis effect is going to influence motion of fluids in the atmosphere and in the ocean. A couple things to keep in mind that sort of were stated here. One thing is that it doesn't matter in the northern hemisphere if a water mass or a paper airplane is moving to the north or to the east or to the west or to the south, that deflection due to the Coriolis effect is going to be constant. So it's not a function of the direction, it's a function of the latitude. And the other thing that's maybe a little counterintuitive is that the Coriolis effect is most pronounced not at the equator, but at higher and higher latitudes. So the way to think about that, I can draw a picture here. So if we think about the Earth, the video is pointing out that looking down from the top, so this is looking at the Earth one side. So here's the North Pole and the South Pole. So and then looking at it from the top, that's the North Pole. The equator is spinning much more rapidly than the top, just like the center of a record. So the difference in acceleration is greatest as you go from zero motion to relative motion. Whereas the difference between the Coriolis effect is greatest in the high latitudes and decreases towards zero at the low latitudes. And so the Coriolis effect is a function of the cosine of the latitude. You can see that here. So, this is illustrating how things are deflected to the right. So in the northern hemisphere, the deflection is to the right, and in the southern hemisphere, the deflection is to the left. Doesn't make any difference which way you're going. So if you're going to the south, you're still deflected to the right. In the northern hemisphere, if you're going south, you're deflected to the left in the southern hemisphere. Okay? So the Hadley cells of the equator describe air which is moving in. There's a subtropical jet in the high latitudes, and relatively cool air is sinking. So the warm air which rose at the equator and was displaced to higher latitudes in the Hadley cells cools off and then sinks. And then that sinking air is, so there's a Hadley cell between about 30 degrees and the equator. There's another a convection cell called the Farrell cell between about 30 and 60 degrees. And then there's a final convection cell called the polar cell between 60 and 90 degrees, 60 degrees in the pole. So if we take our picture of these convection cells and add the effect of the Coriolis patterns, we get these sort of generalized circulation of the atmosphere. So this is driven by rotation of the Earth and differential heating of the atmosphere. There are convection cells and latitudinal belts, and different processes include clouds, precipitation, and these events are changing. Sedimentation, which is rain out, oxidation, photodissociation, and these are processes which remove materials from the atmosphere. Okay, so let's think about how these general circulation patterns might influence different wind patterns. So as the air is at the surface winds are moving towards the equator and then being deflected to the right in the northern hemisphere, there is a sort of net rightward passage, net westward passage. So in historic times, navigators came to understand that there was generally westward transport in the sort of tropical regions. And so if you were sailing from England or Europe to the north, to the Americas, you would find much more favorable winds if you first sailed south and then sailed west. And these favorable winds were the basis of international trade. And so the winds came to be known as trade winds. And so the trade winds moved toward the west. Well, the trade winds moved toward the west in the southern hemisphere as well. Because remember, in the southern hemisphere, things are deflected to the left, and in the northern hemisphere, they're deflected to the right. So there's a general westward trend around of this, created by this Hadley circulation around the international intertropical convergence zone. Likewise, if we move further north, there's a pattern of westerly wind coming from the west and moving toward the east in the higher latitudes. and relatively low winds at what are called the horse latitudes. And so the horse latitudes got their name because ships would often become becalmed. They would run out of wind in this region. This is the region of the Sargasso Sea, for example. And so they were called horse latitudes because horses died when ships became becalmed and could no longer make progress. So if you're traveling from Europe toward the Americas, the best process is to move to the south and then travel westward. And then in the south, if you want to return, you want to go further north and catch the westerly winds moving back toward Europe. And so this process, this circulation pattern promoted triangular trade, so movement from the Africa on the west coast of Africa toward the South America, and then up into North America, and then return toward Europe. Okay, so that's the movement at in the surface of the planet. If we look in the higher latitudes, we can try to understand what's going on with the Rossby waves and jet stream.
Weather patterns are caused by temperature differences in the atmosphere. Those lead to pressure differences, which, combined with the rotation of the Earth, cause air to move around the globe. We feel this as wind. Jet streams are very strong winds in the high part of the atmosphere, anywhere between 5 to 7 miles up. The speed of this stream can be more than 200 miles an hour. These bands of air are typically thousands of miles long and hundreds of miles wide. In the northern hemisphere, they broadly flow from west to east and shift north to south according to the season. In wintertime, the temperature contrast between cold polar air and warm tropical air is greatest. The jet stream is strongest at this time of year. These boundaries are also where weather fronts generally develop. A low pressure stream is like a giant funnel of wind spiraling inwards and upwards, forcing warmish air towards the center and then to rise. As this moist air rises, it condenses to form clouds. Over the North Atlantic, the jet stream typically steers depressions in a west to east direction. A stationary jet stream pattern over the Atlantic will bring frequent depressions to the same region. Sometimes warm air moves further north than normal, or cold polar air moves further south. This can change the prevailing west to east jet stream pattern. This causes the jet stream to buckle, causing depressions to move towards different regions or blocking their movements altogether. Therefore, jet streams can have a fundamental effect on our weather.
Well, let's look a little at the wind patterns presently being experienced in our region. So here is a view from the 9th of February. I'm going to click on this and it should bring us up to a page. So this is predicted movement of wind, surface winds in the northern hemisphere in the present day, and we can see that generally there's relatively mild and weak surface winds experienced, and you can see how these wind patterns form. So there's a cyclonic motion of wind in the, so there's a strong extratropical storm happening here in the North Atlantic right now. And you can see this counterclockwise rotation occurring in the present time. So what's happening here is there's a low pressure region. Wind is rushing in to try to, air is rushing in to try to equilibrate that low pressure region. And as the air rushes in, the Coriolis effect sets it in motion, just like we saw in that diagram. And so we get this circular pattern. So this is this would be a region of very strong winds. It's illustrated by the dark red color and the relative long vectors formed by these winds. So this is what the wind is doing at the present time. In terms of the jet stream, the jet stream, as of today, was showing particularly strong patterns over the Midwest and East Coast, and this is associated with the severe and winter weather that's being experienced right now in those regions. So the motion of the jet stream is caused by this differential in temperature between the colder temperatures in the higher latitudes toward the pole, and but the Arctic region are warming with climate change, and with this warming we're getting apparent changes in the jet stream. So I'm going to show you now a video of the jet stream from NASA. I think I'll show you this. So this is a view from the pole, and this is the jet stream. So the jet stream, which occurs at about 10 kilometers, it's the region of the jet stream. So the jet stream has these meanders, and there are typically 7 waves in the jet stream. These are called Rossby waves. Let's see if we can. So you count them, and you can usually get to 7. They're not always distinctive. Over time, we get, because the jet stream is weakening, there tend to be deeper meanders in the jet stream. So the jet stream reaches further to the south and shows these more extreme patterns than it typically does, or that it has historically. And with these changes in jet stream, we can get severe weather events. You've probably heard of the Arctic vortex. Well, what happens with the Arctic vortex is one of these deep meanders in the jet stream carries with it polar air from northern latitudes, and that polar air can cause extreme low temperatures. Another effect that occurs is that we can have very rapid extreme patterns in the upper atmosphere. And so most of the passenger jets fly right at the top of the troposphere, right where the jet stream is. And so there was in February of 2020, there was one of these deep meanders of the jet stream, and planes flying from west to east were accelerated by the jet stream and made record crossings. And so for the first time in years, in February last year, a commercial plane was able to cross the Atlantic in less than 5 hours because of this temporary meander of the jet stream, which caused very high winds moving from west to east. So the jet stream and the polar vortexes, so as we, in the fall and the winter months, we get these effects. And as the Arctic is warming, these waves in the jet stream are accentuated, and they can drive the polar vortexes into the lower latitudes during winter. So that's exactly what's happening right now. We're having one of these polar vortexes across the Midwest, and so the Midwest is experiencing unusually, unseasonably warm conditions. Okay, do we have any questions? I've covered a lot of material, and I'm going to go on and talk more generally about wind patterns and storms and so forth. But I wanted to make sure that everybody was following along with what I've talked about so far. So I'll stop and ask, are there any questions over the material that we presented until now? No questions. Okay, well, the different properties of air motion create different patterns in the wind, and we can classify these patterns according to typical conditions. And so the different circulatory cells create different wind patterns. So the doldrums are calm equatorial areas between the two Hadley cells. Doldrums, you've probably heard this term, refer to periods when ships became becalmed and would drift for weeks. You know, that was also the origin of the term horse latitudes, so the areas between the Hadley and Ferrel cells. So there's little surface wind in these areas. The trade winds were the surface winds of the Hadley cells, and the westerlies are the surface winds of the Ferrel cells. And so we can, you know, codify these wind patterns. So in the equatorial region, doldrums, there's a sort of a doldrum region right at the equator, the intertropical convergence zone. Pressure is low, light variable winds, you know, cloudy, lots of rain, relatively low surface salinity because the rain continually dilutes the surface ocean waters. Between 0 and 30 degrees north and south, these are the trade winds. The northeast in the northern hemisphere, southeast in the southern hemisphere. The general trend, this general easterly trend, was which, you know, would allow ships sailing from west to east to catch favorable winds in these regions. Dry in the summer, wet in the summer, dry in the winter, and a pathway for tropical disturbances. The horse latitudes, light variable winds, sort of doldrum areas, and then westerly patterns in the southwest and northern hemisphere, northwest in the southern hemisphere. Wet, winter is wet, summer's dry, and then polar fronts, polar easterlies, and then cold, dry air precipitation in all seasons at the surface. So those are the generalized patterns in winds created by warming of the air at the equatorial regions and by the circulation and Coriolis effects. We can talk about some other patterns in winds. So an important circulatory pattern or weather pattern is something called the monsoon. And these are patterns of wind circulation that are seasonal. Areas with monsoons generally have dry winters and wet summers. So monsoonal areas, there's monsoons, monsoonal conditions occur on the western coast of Mexico, for example. Africa and Asia experience monsoonal conditions, dry winters and wet summers. Other patterns would be a sea breeze. So sea breeze is cool air from over the water moving on land. Sea breezes typically occur after sunrise, and land breezes occur after sunset, when water that's warm, air that's warmed by the land blows toward the water. We can diagram this as follows. So a sea breeze occurs as the sun begins to warm the air over the land, and of course the land warms more rapidly than the water does, and so when the sun rises, the land warms up first, and as it warms, the air over the land rises, and in order to replace that rising air, there's a onshore flow of wind. So a sea breeze, a breeze coming from the sea, and that starts at with the sunrise and increases towards the evening. Well, the opposite occurs, the land breeze occurs as the sun goes down and the earth cools. And so you have, with this cooling process, the cool air sinks, descends, and flows offshore to displace the relatively warmer air on land, offshore. And so if you remember what we talked about last week, we were talking about the thermal conservation of temperature, conservation of heat by water, the fact that the thermal inertia of water, of the ocean, so ocean tends to retain its temperature for longer than land does. So this difference, this thermal inertia, means that changes in temperature with during the course of a 24-hour cycle are going to create relatively warmer conditions more quickly over the land, and then relatively cooler conditions during nightfall. And its differential causes air to be set in motion. So sea breezes during the day, land breezes at night. Well, when we have different patterns of air motion because of different temperatures, we can generalize these to understand what happens when we have cold fronts and warm fronts. So here is a diagram showing the motion of a cold front.
This animation is going to describe how precipitation happens at what are called cold fronts and warm fronts. These are weather systems that develop wherever masses of cold air collide with masses of warm air. And the name actually comes from war, where armies would meet along a battle line called a front. And one way to think about the difference between cold fronts and warm fronts is to think about which mass of air is going to win the battle. So we'll start with a cold front. This is a situation that happens where cold air moves in like a big wedge underneath warm air. Cold air is always heavier than warm air, and so it's denser, and it's going to tend to slide under the warm air and push the warm air upward. Anytime you have air rising upward, it's going to expand and cool and lose its ability to hold moisture, and this will give you a band of clouds and precipitation along the cold front. On weather maps, if you watch the weather on the news, you can see cold fronts marked by lines of blue teeth that point in the direction the cold air is moving. Along cold fronts, you typically have very intense local thunderstorms and rainstorms. So it might pour rain for a short time, but then quickly, usually within an hour or so, the front will have moved on. So a cold front is where the cold air pushes underneath the warm air, and you have high rainfall and usually intense thunderstorms. Now, the warm front has in common a couple of things with the cold front. One is that the warm air still goes up on top of the cold air, but in this case, the warm air is actually pushing the cold air out of the picture. So the warm air is winning, and that's how you can remember it. It's a warm front. The warm air pushes against the cold air, squeezing it out. Like imagine squeezing a watermelon seed between your fingers. It kind of squeezes out, right? And as the air pushes, it also rises up over the cold air. Rising air, again, loses its ability to hold moisture, and you tend to get clouds and rain. Along warm fronts, you typically have more mild, more mellow more spread out rainstorms rather than really local intense thunderstorms. And if you're looking at the weather on the news, they mark warm fronts on maps with red half moons that point in the direction that the warm air is pushing the cold air. So that's cold fronts and warm fronts, major precipitation belts in many places on here.
Okay, so there's a sort of a generalized overview of warm fronts and cold fronts and how the interaction of the warm front with cooler air or the cold front with warmer air produces not just patterns of motion, but also precipitation and different precipitation events. And so the cold fronts that are being experienced in the Midwest and the Northeast right now are producing intense precipitation, but that precipitation is falling because it's wintertime in the form of snow. So we're getting record snowfalls or very high rates of snowfall in the Midwest right now as a result of this polar vortex, which has descended over and which is, so there's a large cold front which is displacing warmer air and producing these high rates of precipitation. So we've seen ways in which storms can interact. And so if we have cold air and warm air moving in the atmosphere across a front, so the cold front is the teeth, the sharp teeth pointing in the direction of the cold front, and the half moons or the semicircles are the warm front directions. So if we think about a storm, we get motion like this. So there's, cold air moving along the cold front and warm air moving on the warm front. And at the center of that motion is the low. And that low is typical for storm events. So this pattern would produce a tropical cyclone in the northern hemisphere and could lead to intense storms. So storms are generally regional atmospheric disturbances. They have high winds and most have precipitation. Tropical cyclones occur in tropical areas, and these storms can cause intensive damage and destruction of property. The extratropical cyclones occur at the Ferrel cells, and these are winter weather patterns. So that storm that we saw, that cyclonic storm that we saw in the map of winds that I showed earlier on, that was an extratropical cyclone-like disturbance, and it was occurring at the Ferrel cells, sort of in the higher latitudes. Both of these kinds of storms are cyclones, so they're rotating masses of low-pressure air. Okay, I'd like to stop now, and we'll go back and cover some of this material on our lecture on Thursday. But what I'd like to do now is to open up the, so this week your milestone 2 is due. So I'd like to open up the breakout rooms and go ahead and have all students enter into the breakout rooms and give everybody a chance to talk about your milestone 1 criticism and how you've revised milestone 1, and give you a chance to plan for milestone 2, which is the literature research that you're going to need to do for your project. So I'm going to open the breakout rooms. Please go into your breakout rooms, and then Carrie and I will come and visit. Let's see. Okay. Okay, looks like I have some folks here who have not been assigned. So Jacob, Brandon, Carrie, do I need to assign you to a room?
No, I can get in. I was just looking for a milestone 2 to add it to the modules.
Okay. Jesse, do you need to join a room? Brandon, Nelson?
It looks like they both have access to their rooms, but they're just not joining them.
They may not be following along. All right, let's start at group 1, and if you go into join like group 11, we can work our way down, okay? Well, hello, group 1.
Hello, Professor.
So,
Hello.
hello. So remind me of your topic that you're doing for your team project.
We're doing the acidification of ocean, and I think we narrowed it down to on corals.
On corals?
It's on the acidification of coral reefs.
So the effect of ocean acidification on coral reefs.
Yeah.
And, okay, so that's a good topic. And have you looked in the Web of Science, or where do you think you'll look for? Have you started your literature search?
I know I was looking at like Science Direct a little bit here and there, and just like the FSC library, but I know some other people were looking at other places as well.
Well, let's see, maybe I can look on Web of Science here with you all. And so if we say ocean acidification, I'll share my screen. So if we say ocean acidification, and coral reefs, say corals. Actually, you don't need quotes, it's just one word. And we'll search, and I bet you there's a bunch of terms that come up. Look at this, 184 pages. So that's 1,840 approximately findings. So you want to try to narrow that search down a little bit. So if I look at review articles, that narrows it down a bit. We get about 172. So let me do that. Coral reefs under rapid change and ocean acidification. So here's a paper. This is from 2007, but it's still relatively current. So that would be something that you could definitely look at. What else have we got here? Ocean acidification, the other CO2 problem. So this lays out, why ocean acidification is occurring. So that would be a good thing to read. Climate change impacts on marine ecosystems. This will talk about, the way in which different marine ecosystems, not just corals, are being affected by climate change. That would be a sort of a more general one. Projecting coral reef futures under ocean acidification. This is so here's another one. Reefs at the deep, the biology and geology of cold water. So these are, if you want to think about corals, I think it would be really helpful if your group would consider not just the corals that occur in shallow water, like Keys, but also deeper water, because the rate of acidification and the impact on corals is going to be very different from the acidification is occurring most rapidly in the shallow waters, because that's where the greater accumulation of CO2 occurs, okay? So if you'll just, follow this pattern, which I did there, and do that yourself, I think pretty quickly you'll come upon some very helpful articles, okay? Any questions about how to do that? And so what you want to do is you want to come up with about 10 or 12 actual research sources. You might also, at the same time, you could try, doing a search, just sort of a Google search on corals and acidification. So this is not looking at the Web of Science, but this is sort of a more general view of articles that are about the same topic, but being presented not as peer review articles, but as articles for the general public. So a lot of the terms that you'll find get explained in simpler terms if you refer to these things. And a lot of times, the other thing that you find in popular articles are sort of better illustrations and things that are easy to understand. So I'm going to leave you now and go on to some other groups, but let me suggest that this is something that you could do individually, and I think you'll pretty quickly come up with, because of the topic that you've chosen, I think you'll come up with, quite a number of helpful research sources. Okay.
Excuse me, Professor, before you go, do we have to present our sources in like an annotated bibliography or anything like that?
Absolutely, absolutely. You have to, present your sources. So what I'd like you to see for this, and I think that's in the assignment may not be open yet, but we'll put it out there. I'd like each of those sources to sort of be listed, with a bibliographic entry, and then I want you to annotate that, sort of explain, what aspect of your research each individual source is going to cover. And you can also think about the, the overarching themes, climate change, impacts of society, scientific consensus, and so forth. Okay.
Professor, how long do you want those annotations to be?
Oh, brief. A sentence or two is plenty.
Oh, okay. And for the citations that we'll have in our source, do you want a working link for every source, even if it's a journal or a book or something?
I don't want links at all. Links don't help. What I want to see is a properly formatted bibliography, so that each of the sources has a citation, because that's the citation that you're going to use when you write your paper.
Okay, thank you.
Okay. All right. Well, let me get out of this. Okay. Hi, here I am. I think you asked for help.
Yeah, we just had a question about, because I read on the syllabus that we need about 25 sources for the paper, but then I think I remember we saw somewhere that it said 10 to 12.
Yeah, it's somewhere between, so 25 would be an upper end and 10 to 12 is sort of a lower end. And the requirement is that you have to have, I think, at least 12. And those 12, they have to be at least 10 peer reviewed. But depending on what topic you're researching, you're going to want to expand beyond that. So what was your topic?
It's on the coral reef I have it written down. I forget what it's called, but it's a big barrier reef off the Philippines.
Oh, okay. So, and what do you, okay. I don't remember, I don't know what that's called, but have you done a literature search on this? Have you looked in the Web of Science or anywhere else for?
We have not yet.
Well, let's try to do that while you're online. So let me share my screen. There's another group that's doing coral reefs. And so I was looking up different sources, helping them find different sources. They're interested in looking at the effects of ocean acidification on coral communities. And so the search terms that they were looking for were ocean acidification and corals. But you're interested, so what is your, so they've done a good job of sort of narrowing down the way in which that they're approaching this very large topic of corals. What sort of focus does your group envision taking on corals?
I think we want to focus on how, just as a resource, how it affects the people and the animals living in the reef, or the people near the reef, how it helps them, or how they utilize it.
Like how we, like our first thing, the milestone we turned in, we wanted to do living marine resources, but then Carrie said that was too broad. So we sort of chose this coral reef, and we were going to explore how they, the community and maybe the industry around there used it as a living marine resource.
So you don't know the name? Because I off the top of my head, I don't know the Philippine coral reef.
Oh, it's the Apo Reef, APO.
APO?
Yes.
Apo Reef. All right, well, let's try putting in Apo Reef. Sorry. Let's just try Apo Reef and see what we get. Okay. So there's not a lot specifically on the Apo Reef. Time averaging taphonomy. So this is a way of classifying regions and habitats within the Apo Reef. Primary and observations. So this is what you got. The Philippine.
Looks like we might have to switch to the Great Barrier Reef. I just thought we would try something a little bit different, but there's not much.
Well, why don't we go back to our search and see what are you, so it sounds like you're interested in sort of the, fisheries management, resource management, and coral reefs. So why don't we say coral reef and resource management. Is that kind of where you're interested in going? Does that kind of capture what you say?
Yes.
All right, well, let's try that. Okay, we do a lot better here, don't we? There's lots of stuff. So we can do our usual trick. We've got 12 articles that are review articles. So if I refine this list, I get a bunch. Emerging frontiers and socio-ecological systems for sustainability of small-scale fisheries. Intrinsic vulnerability of fishing of coral reef fishes and their differential recovery in fishery closures. Okay. Coral reef fishery stock assessment model. So you see where you go here. This gives you, so here's a highly cited paper. And this deals with sort of management aspects of the topic. Sea cucumber fisheries, global analysis of, now that may be, a little bit more specific than specifically, you wanted. These are all being sorted in terms of time of the numbers of times that they've been cited. Okay. So that was a way to do that. If we do a sort of a Google search on coral reef, artisanal coral reef fisheries, you can see that we've got, patterns and artisanal fishing, and that's a sort of a technical term. An artisanal fishery is one which is practiced using sort of non-industrialized methods. So artisanal fishery are sort of the traditional fisheries practiced by indigenous peoples is a good way of describing it.
Sorry, my internet kicked me out of Zoom. I didn't hear the last bit of what we were talking about.
Well, when did you drop out, Tara?
So you were saying how we could focus on, because I said that there wasn't a lot to go from for the Apple Reef, so I suggested maybe the Great Barrier Reef, and then you were talking about how we could study like the fisheries and how.
Right. So what we did instead of Apple Reef, I went to coral reef and resource management, because it seemed like the reason that you were interested in the Apple Reef was because you could look at the way, sort of developing countries could interact with their resources around coral reefs. Okay.
Yeah.
So the search terms that I used were coral reef and resource management. And if we search along those terms, we get a lot of articles. So there's like 200 articles. But if we refine our search and we look for just review articles, so there are 12 review articles. And these are being cited by the number of times they're cited. So here's a paper that was cited 206 times. Integrating customary management into marine conservation. So you can see how this goes. Okay, so those are methods that I would use in Web of Science for getting peer-reviewed sources. And then I suggested that you might look for artisanal coral reef fishery. Because an artisanal fishery is one that Tara, I think you need to mute. An artisanal fishery is one that is practiced, not using industrial techniques. So it's not, it's a sort of a traditional fishery. And so, patterns in artisanal fishery. If you'd read down here, you can find, these are mostly scholarly articles. If we look for news, you can find, lots of different articles, that approach that. Well, here's one: East Africa's reefs being fished at unsustainable rates. New study shows that fish stocks and coral reefs on the coast of East Africa have been fished to worryingly low levels. So that's a way that you can, get access to sort of results that are not necessarily peer-reviewed, but that are pertinent, relevant for your topic. Okay, does that make sense, guys? Yes, no?
Yes, it does.
Okay.
Thank you.
All right, let me go to a different group then, and hopefully that'll help you. Okay, I guess we're just about out of class time here, but I did want to give you a chance to, help you out with your research and help you out with this milestone. Is everybody there? Okay,